Thank you. So it's time to start with our keynote speaker, Mathias FINK. So Mathias is the ultimate interdisciplinary person. He's both a mathematician, a physicist, a communication person. He worked in the US, in France, at ESPCI. He founded Institut Langevin. It was not called at the foundation exactly like that, but this a key institute on electromagnetism is his creation. He's extremely well known for his work on renversement temporel, which is time reversal, which is a key thing in. So he can create an electromagnetic spot at this time, at this locus, and this for all types of waves, and there's activities in acoustics, in optics, in communications. And this has lots of applications in a variety of fields, in medical imaging, for instance, in communication, as we will see. So Mathias got, a large number of awards. I will not mention all of them. But the Prix Louis Nel and the Helmholtz Prize also is Helmholtz Rayleigh Prize, right? So medal, and that's a very important dimension of his work. He's the founder of 6 startups, and some of them are companies now, and including Greener Wave, which is very active in the field, which now employ more than 400 persons. And so I'm very glad Mathias accepted to give the keynote lecture on of this workshop. Mathias.
Thank you, Francois, and thank you for the organizer to invite me. It's a pleasure to be here and to speak about RIS, reconfigurable intelligent surface. As you see, I put in the title ultrawideband RIS, and I add from acoustic to electromagnetism. In fact, reconfigurable intelligent surface exists in many different areas of wave physics. You have here on the left side RIS for electromagnetic wave, and we will speak mainly on this. And the first RIS were built, I will say, in our lab in 2013 to try to modify the environment to focus a wave automatically on one smartphone. This is RF signal. Now, it exists also RIS for sound wave, acoustic sound wave, and in fact, it has begun later in 2017, and there was some work in Hong Kong, especially, and I will speak of this work, to build RIS in a room to reconfigure the way sound is going through the room. But in fact, before these two kinds of RIS, there was quite before in optics what is called spatial light modulators that can use liquid crystal matrix, where you can control the reflectivity of a matrix of liquid crystal. It is like you have a mirror, and you can control the way the mirror reacts on each pixel. And this spatial light modulator, which is called SLM in the field of optics, are used a lot. And in fact, the first nice experiment who was done in optics was in 2007, and I will show you how this was working. And if you look this, there is a chronology. Things begin in optics, after it goes to RF, and after to sound. But before all this, there was something else. And in my lab, we were working on ultrasound. Okay, you can have RIS for ultrasound. Very difficult to build RIS for ultrasound. But in ultrasound, we have something very interesting. We can have an active array, which is active. It is not a passive device, made of 100 or 1,000 piezoelectric transducers. And each transducer can be controlled in transmit, in receive. And the electronic is not so high frequency because it is megahertz and not gigahertz. And with this, you can try many things. And we developed a long time ago, here it is 94, but it has begun before the concept of time reversal mirror. It is a mirror made of an active antenna where each element can receive, each element can transmit, but what comes when you receive the data are digitized and put in memories. And this was possible only in the 90s. Before, you have no memory big enough to play with this, and the concept was impossible to exploit. But in the 90s, memories appears, digitization appears, and you can play with what we call the mirror. And in fact, the idea was the following. Imagine that you have an antenna that sends a short pulse. This is ultra-wideband pulse. This pulse contains many frequencies. You go through a very complex medium. We call this a diffusive medium made of many obstacles. And you collect on each of your receiver the signal that is coming through this medium. You put all the data in electronics memories. It can be very long because you have multipath in the medium. And after, you take all this data and you time reverse all this data. What you receive first, you send last. And now the antenna become transmit antenna. And you send back all this data and you look what come back at the origin. And even if when you send a short pulse, the pulse become very long because you have a lot of multipath, when you do the time reversal process, what come back at the origin is very short. You recompress the signal in time. You send very long coda, but you have a very short signal. And better, this is what I call time focusing or time compression. And better, if you look the focal spot, you have the size of the spot you create. Here it is the red spot. This spot is much thinner than the spot you will do if you have no diffusing medium. If you have just open space, free space, you will have a spot which is very large, but when you introduce this medium, suddenly the spot becomes very thin. Okay. Ah, okay. Oh, sorry. Il n'y a pas de partage d'écran. Alors, well, sorry for people who are connected with Zoom. They don't see anything. Okay. Okay, I come back on this experiment. You see it? Yeah, you have a source point sending a short pulse, ultra-wideband. You record it. Now you time reverse what you record and you send back. And the pulse is compressed in time, but it is also compressed in space. And what you have with this experiment, which is quite interesting, is that the focal spot has a size that does not depend on the size of your antenna. It depends only on the size of the diffusive medium. It is like you have transformed a complex medium in a lens. The medium becomes a lens, and if the medium has a lot of scatters, the lens is huge, and you can have, in fact, a very small antenna, but it will behave like a very big antenna because of the medium. And we demonstrate this with ultrasound. And after we use this to do what we call time reversal communication, the goal was to send through this kind of medium different data to different guys which are very close one from the other. And because you have a diffusive medium, the focal spot becomes very thin, and you can have access to a lot of channels which are nearly orthogonal, and you can have much more information transfer through a diffusive medium. And time reversal was a nice solution to do this. When we have done this, it was in the 90s, our colleagues in optics were very jealous of us. And we have a meeting that we create, that we do every year in Cargès, in Corsica. And our colleagues from optics were jealous, and they say, we have to do the same in optics. And in fact, in optics, they cannot do time reversal with many antenna that they control. It's much too expensive, but they have in optics mirror. And in fact, what they do, they have this spatial light modulator, And our colleagues, especially in Holland, Alarmosk, decide to learn how to focus light through a diffusive medium. A diffusive medium, it's a piece of paper. When you look through a piece of paper, you see nothing. But in fact, if you send light, light can go through this and light become completely random after. And it is called speckle noise that you see when you use a laser pointer through diffusive pitch. You see a lot of bright spots. And the idea of Alarmosk was to use an SLM to reshape the shape of an optical wave coming from a laser. And instead of seeing this kind of signal, he wants to focus on one spot. And I just move this because it may. And what he is doing, he tried to find the best configuration of the SLM. And at the end of the day, instead of focusing everywhere light, it's focused on one spot, and he become to look through a diffusive medium to focus. And they have done this, and they found the same result that what we found in ultrasound, except this is narrowband. In ultrasound, time reversal is wideband. And after, in our lab, we were playing the same game in optics, and we decided not to create one bright spot through a diffusive medium, but a series of spots. And like this, we put a diffusive medium, we have a laser, and we have an SLM. The SLM reshape the wave profile to create 3 spots or 4 spots or n spots. And after, you can add modulation. And we demonstrate this. It was we demonstrate this. And at the same time, we were interested by electromagnetic time reversal in the lab. And with Geoffroy Le Roset, we were doing electromagnetic time reversal. And suddenly we say, I was in Brittany, not happy with my phone that does not get enough signal. And I was thinking, if I put in a wall a kind of mirror, a copper mirror that I can reshape to make that all the waves that come on the mirror are focused on my telephone, I will be happy and I will have signal. And I called Geoffroy to tell him, I have an idea. Perhaps we can create not an SLM, spatial light modulator, but an SMM, spatial microwave modulator. And I come back, it was in 2013, and with Geoffroy, we decide the best way to make a spatial light modulator, a spatial microwave modulator, is to make a modulator with 2 phases. Reverse the phase, not reverse. It is a very simple phase control. It is a binary phase control. And we begin to develop this. And the story for us begin like this, and I will speak of this more after. But now I come back on physics. I come back on the general problem of communication between 2 points. Now it is not time reversal, it is communication between 2 points. Shannon capacity depends on the SNR that you have at point B, where you receive a signal coming from R. If the distance between the two is big, you have a poor energy efficiency, and Shannon capacity is not good. But you know that if you live in a magic room where you have boundary, it is no more free space, but you put these 2 antennas at the 2 foci of an ellipsoidal room, where the room is a cavity, a reflecting cavity. And if you are doing this, and this exists for sound wave in the Paris metro, this is an example, but there are better examples. In this, if you speak at the good position very weakly, the guy which is just in front of you at the other foci listen perfectly what you say. You say, and nobody else listen. And it is spectacular with sound. But it is not obvious to live in such a context all the time. And when you have the ellipsoidal focusing process, if the ellipsoidal is transformed in a sphere, what comes from R come back on R. This will be a time reversal mirror. But if you have an ellipsoidal mirror, what comes from R go on B. it is not a time reversal mirror. It's a mirror that sends back. And you will see the connection with time reversal after. Now, this technique of focusing is valid for narrowband signal or broadband signal, because it's just a delay. All the delay between A and each point here and B are the same due to the property of an ellipsoid. And in narrowband, in fact, what you have is just a summation of all the Fresnel vector coming from all the paths. It gives you a big signal. Now, the model has some limits. If the wall is very hard, it's perfect. But the wall can be a medium which is not hard, and it can create surface waves that move at a speed which is different from the speed that you have inside the medium. And in this case, the focusing is not perfect because you have non-locality. You have a kind of coupling. What comes from A does not go back only from A at this point, but it can move and go from another point. I will come back on this because this is very important to explain the connection in RIS, which is the phenomena of non-locality. But usually, if a wall is very hard, it is very good. And the diameter of the focal spot you have at B is λ/2 if you send one frequency. Well, this is an ellipsoidal room. Now, it is interesting to ask the following. Can you create a room that connects Mr. A to Madame B and Mr. C to Madame D at the same time? That is to say, can you create a geometry which is the superposition of two ellipsoidal rooms? Why not? But the room cannot be complete ellipsoidal each time. It is just a portion of ellipsoidal room. And you can ask how many, if I am a good architect, how many the ceiling can be modified, how many ellipsoidal can I superimpose to know how many couple of connection can I make. But of course, making a true room is difficult. But if you have a room which is digitized, because it's a smart room with some RIS, it is the same problem. You replace the boundary of your room by a virtual boundary where you have many pixels and you can control each pixel, and you ask, can I superimpose two ellipsoidal on this pixel array? And it can be done, of course. I will show you this. Now, we were interested by this problem for sound. Can I have a room, for example, where two guys speak to two other guys, and I modify the boundary of the room in real time to make that there is no more of a cocktail party effect, which is very difficult when many people are speaking in a room. It's a nightmare. It would be very nice if I speak to Francois and another people speak to another guy, and nobody else listen to what each guy says. Well, and you will see that we have done this recently. And we have the same problem for electromagnetic wave. If you have many antennas that transmit the wave, many that receive, can you change the boundary of the room to optimize connection between all these antennas? Here, it is what I call mu-MIMO. It means that each guy wants to speak only to another guy, but you can do MIMO, classical MIMO. You have many antennas that transmit to many other antennas, and all of them speak together, and you want to maximize the information that you can send. This is this problem. How many antennas can I play? Now, if I come back to the problem of only one couple of people that want to speak one to the other, but I can do this the follow. I can look this, and this is the work we have done in 2014 that we called at this time shaping complex microwave with tunable metasurface. And the idea is to have any complex room, to put a boundary, and to transform locally the room in an ellipsoid. Of course, it is not a huge ellipsoid. It depends on what part of the boundary you put and how big is your RIS. But the idea is ellipsoid. Ellipsoid is the unique idea. Now, usually, the smart metasurface you are building are sampled with typically half the wavelength, which is that contain enough information to be sure you completely, you can work on the field in the best way. Now, there are two aspects of this kind of communication. Or you are narrowband, and this is what exists for 5G typically, or you are very broadband. Narrowband, what it means? It means that you send a bandwidth, the signal bandwidth is less than the coherence bandwidth of your environment. And I will come back on this. Broadband, it means I send many frequencies. For each frequency, the phase control is very different from another frequency. And when I have many frequencies, how can I control the best phase for each frequency? And sound is really narrowband, broadband compared to RF. When I speak of narrowband, it's relative narrowband compared to the central frequency. Now, you know that typically when you are in any complex environment, when an antenna emits at one frequency, when you look the pattern everywhere, the pattern is relatively random. It can be a relay distribution. It depends on the statistic of your room. And you have bright spot, black spot. And you know that two things determine this. The coherence length, it means it is the size of each grain of light, each bright spot. And the coherence bandwidth tell you that if you change the frequency of your emitter from a given delta omega, the speckle pattern change completely. And you look how much you have to change to have a new speckle pattern. If you work in a bandwidth which is, smaller than delta omega, you are sure that you can control things only at one frequency, and to control the phase, it's just phase at one frequency. Now, if we are narrowband, well, the idea is very simple. I have an antenna alpha. I want to send, for example, to beta. It is the case of one guy. And I want just to put a reflectivity here that optimize this connection to make that all the data coming from alpha arrive in phase on beta, if I am in narrowband. Now, there is a very important problem. When you speak of MIMO communication, usually you speak of two sets of antenna, the transmit antenna, the receiving antenna. And usually you speak, you have a bandwidth smaller than the coherence bandwidth, and you define a transmission matrix made of complex numbers that describe propagation between two sets of antenna. When you are doing this, physicists call this Green's function between each point. But you are making an assumption. When you are measuring the transmission matrix H between alpha and beta, you assume that when you measure on beta, what you have on another antenna close to beta does not interact with beta. You make the assumption that your antenna that receive signal have no connection between them. That is to say, when alpha emit, if there is only a guy in beta that receive, what you have on the other antenna does not play any role. Your other antenna can be at zero, can send energy. You don't care. You consider that you have a pure matrix, an ideal matrix between ideal points that transmit, ideal points that receive. And this is true in many applications when the antenna are well separated. If there is no mutual impedance between antenna, this is completely true. Now you have a problem to define a matrix in this configuration. You have transmitter here, alpha, and now you have a RIS. A RIS can be considered in some way as a set of antenna, but it is not true. It is a set of points. Each point must have a nice reflectivity, typically 1 as the modulus of reflectivity, but you can control the phase. And in this case, if you want to define a matrix between each antenna alpha and the RIS point, is it easy to do this? Not really. Why? Because a RIS is a panel made of many small electronic circuits, passive circuit, small resonator. but each of them has a big reflectivity. That is to say, when you measure what comes from alpha on the point I, in fact, it depends on point G. Why? Because if G is on the state +1 or -1, if you have obstacle in front of this, there is a connection G. When you change G, there may be a signal coming back and meeting an obstacle and coming on E. What comes on E does not depend just on E. It is coupled to another element G, because these elements are strong reflectors. They reflect a lot, and if there are obstacles in the vicinity of RIS, there is this coupling matrix that come and create a big disorder. And in fact, what you receive on E does not depend directly on what is coming on E, like there is no other RIS, but it's come back also from the other RIS element through a matrix that connect E and G. And this matrix is called, in our field, the reflection matrix. It is like you have many antenna E and G. When antenna G emits something, if there is an obstacle, there is a reflected wave that comes on E. And this is called, in radar theory, this antenna, the bistatic radar, that is to say, or the multistatic radar. That is to say, the definition of what arrives from alpha on E depends on what you have on G. And it makes things very complex. And you can define what I called H0 of E and G. This is the reflection matrix that connects each element of the RIS one with the other. And you can also speak of H0 of alpha E. This is the matrix that you will have in absence of a RIS. All these three matrices are the one you have in absence of a RIS. It is like you have ideal point at the good position. And because of this, the full description of the RIS may be quite complex. And in fact, if you look exactly what you have, if alpha emits something, there is what is coming from the medium directly on to beta. Beta is the receiving antenna. And there is what is going here. And if you look what you receive on beta, you have what you have sent from alpha multiplied by H0 alpha beta. This is the part that go through everywhere except the RIS zone. It is like there is no RIS. But now you have also what you send to alpha to E, and what you send from E that come back on beta. And what come back on beta is the reflectivity you have on element E multiplied by the signal you receive on E multiplied by the H0 beta E matrix, the one that connects here from here. But the signal you receive on E is not only the signal that comes of alpha, but the signal you receive on E is the signal that comes of alpha plus the signal that comes from the other G element. That is to say, you have an introduction of this matrix that connects, and this matrix for each HG, it can be written in the same way. And when you have all this mess, you can add all this, and at the end of the day, what comes from alpha to beta is what you have directly without the RIS, plus this recursive connection where H0, what we call the reflection matrix, play a role. And in the general case, it is a very complex story, which has a very nonlinear behavior. When you change E or G, it is the way you change the channel is not very linear, because the way the boundary change, if you change one pixel or another pixel, you cannot say that what you observe is the sum of the two effects. Because of this reflection matrix, it's much complicated. And in fact, you can play with this. Philippe Hugnes will make a nice talk tomorrow on this problem of this multiple connection. And what you receive on beta coming from alpha is given by this story, which is quite long. Now, if a non-locality problem does not exist, it means that if you have no obstacle close to your RIS, things can be simpler. And in this case, if there is no obstacle close to the RIS, and if the RIS is not too big, you have a much simpler way to write things. What you receive from alpha on beta is the direct path going, but is not going through the RIS, plus what is coming from the RIS, but in this case, the reflection matrix has disappeared and it is simpler. Now, in this case, in the assumption of local reflectivity, it means that I consider that I have no reflection matrix between E and G. That is to say, E and G are far from any obstacle. The obstacles are very far in the room. In this case, I can write things like this. What comes on beta is what is coming through the space without touching the RIS, plus what is coming from the RIS in a very simple way. And if I can define a matrix element between antenna alpha and E and antenna beta and E, the way to optimize things is very simple. You want to have a maximum signal on beta. What is the reflectivity pattern you have to put here? But you have just to put here in the non-local, if there is locality, and if you know the response between alpha and each element E, you have just to put the phase conjugation of this. The reflectivity here will be the product of the phase conjugation of the matrix element between alpha and E, multiplied by the phase conjugation of the matrix between beta and E. And you write this, and this is what we call a double phase conjugated mirror. When you do this, you guarantee that all what is coming from alpha, when it's arrived in beta, the phase conjugation has made that all the phases are equal, and all these signals add together. Now, you have also what we call the direct path, the H0 alpha beta, that does not go through the RIS. And now it gives you another contribution. And because there is a phase angle, you have just to add minus G phi. And if you put just this reflectivity, when you have a RIS mirror, which work with locality, not too much obstacle in front of this, this is the best mirror you have to connect alpha and beta. Okay. And now what we do is that we simplify. Instead of having a perfect phase law, and we prefer to have just a binary phase law. And if we have many Fresnel zones in our aperture, it means many zones where the phase change, and we cancel this phase change, you can have a very good focusing on point beta. Okay. Now, when we were interested by this in 2014, we built the first RIS, and Geoffroy Roset, which is here, built this first RIS, and the idea was very simple. We have a resonator that we put on the surface of the RIS. When you have an incoming wave coming on a resonator, if it's come at the frequency of a resonator, the wave is shift of pi over 2. It's a property of resonator. And if you have a ground plate, the wave after is shift of pi. And it comes back in the resonator. And like this, if you send an incident wave at the same frequency that the resonator, the full path you have in reflected mode is shifted by 2 pi. It is like you have no shift. Now, if you just change the frequency of a resonator from a small amount, now it is not true, and you have pi. That is to say, it is easy to make a two-state resonator, and the idea that we have was we have a static resonator, a parasitic resonator, and we have a switch or a diode that allow to connect one from the other and to change just the frequency. And this is the way we build this. Now, what is interesting is that with Geoffroy Roset, we create a company, Greener Wave, in 2015, but nobody was interested by RIS. And during 5 years, everybody was, nobody wanted to give money to the startup to become a big startup. And something good happened. Mr. Di Renzo and other people begin to discover RIS in the 19, something like this. And they begin to speak of this all around. And the RIS community came. We were not calling this RIS, we were calling this SMM. Not very exciting, but RIS made it. And suddenly the company became stronger and stronger and begin to build RIS at many frequency and begin to develop many kind of RIS with 1,000 components and begin to found things which is better than diode to have a very low consumption. And typically today, we have a RIS panel with 3,000 elements that consume nearly 2 watts today, which become really interesting in terms of low consumption compared to active antenna with many antenna. And we are playing the company, 85 people now in Paris, and it is growing very fast. Now, I explain you how we do a RIS for microwave just by using electromagnetic resonator that will change the frequency of a resonator. You can do the same in acoustic. In acoustic, resonators are typically box. And we speak in acoustic of Helmholtz resonator. It's a box. If it is a given volume inside and a given surface and a given size for the neck of the box, there is a resonance frequency of the box. Typically, when you take a soda can, if it is empty, a soda can resonates at 440 hertz. You say, if you send 400, you see the soda can begin to be a good resonator. Now, if you want to change the frequency of a resonator, you have to change the volume of a resonator. And if you have a small motor, you can make it. And with my colleague Wang Kung Ma in Hong Kong, we begin to build this kind of resonator, and we begin to create wall of this kind of resonator where you can change things. And these resonators are interesting because they allow you between 1,100 hertz and 1,600 hertz to change perfectly, to shift the frequency, to shift the phase, to have. And in fact, it's interesting because here the bandwidth on which you can make the +1, -1 is much higher than the coherence bandwidth of a room. And the question is, can we play with this with music or with sound? Okay, now I show you how you can make RIS electromagnetic, how you can make RIS in acoustic, and you don't want to measure all this matrix to optimize RIS. The best is to optimize RIS to have something which is a learning algorithm where you don't need to measure all the element of matrix, and typically what we were doing in the past in the lab was to have an algorithm a la MOSC. MOSC is the guy in optics that try to optimize the way light can go through a piece of paper to focus on a point. And it was a simple algorithm. He tried to change X pixel, see if it is good. If it is good, he keep it. It's allowed to have better signal. After I go to another pixel, and it was something that takes some time, but can be relatively fast. And we begin by doing this. And we play with this algorithm, and here it is Fabrice Lemulti in 2000 that tried to find the best configuration in a room to have the maximum signal on an antenna, and he will move the antenna in the room to be at a point where the field is not good, and the room is, well, the boundary is working to improve the connection, and you see always the pattern you have. Well, it was slow here because it was a long time ago, but at least we know that we can reconfigure our room, which was to maximize what's common on one antenna. Later, with Philippe Delhomme, during his PhD in the lab with me and Geoffroy, we look how we can change a room, but for MIMO configuration, not from SISO configuration. And we know that Shannon capacity depend of the transmit matrix H, and it depends, in fact, of how many singular value of good value you have in this matrix H. And in fact, you know that Shannon capacity is optimized when when the number of singular value is the maximum, and when all the singular value has the same value. And it is, and you know that typically, if you have here 5 antenna and 5 here, the best is when you measure this matrix is to have a flat singular value spectrum. And to do this, the idea is to maximize the effective rank of the matrix. This is the way to optimize Shannon capacity. And in fact, it means that you want to minimize the rank minus the effective rank. And the effective rank is defined by this formula where sigma prime E are the singular value of your matrix. And the objective is to do this. And we show with Philip that we can optimize MIMO connection in my office by playing with the boundary. Okay, now can we do the same with sound? And here it is a 200 pixel wall, 2 parts of the wall here with this pixel. And here, the coherence bandwidth of the room is small, 9 Hertz. It's a room where there is a lot of reverberation. And here you have 2 microphones that can send 2 sources of music, and you have 2 guys. Sorry, no, it is not the microphone that sends music. You have 2 sources of music that send different music, and here you have 2 microphones. And you ask, can I change my boundary to really have a good musical connection between each? And the idea is not only to maximize Shannon capacity, but to say to have an effective rank of the matrix equal to 2, because here it's a 2 by 2 problem, but you have 200 pixel elements. But you want also to minimize the crosstalk, that is to say, you want that the matrix H that relates the point is a diagonal matrix, because you want that there 1 send to 1 and 2 to 2, but you don't want to cross. And your objective function is now not only to maximize Shannon capacity, but to maximize the degree, or to minimize the degree of diagonalization. And we play with this. And there is an iterative algorithm that takes some time. And what I want to show you is the following. Imagine we send different music notes. What I have to activate? Yeah. Okay. Okay. No, it is no more meeting. Yeah. Ah, okay. You have. Okay. Okay. No, I will do it. Okay. Sorry, I have not seen that you have. Okay, I come back. Sorry. No. Sorry. This is Do. This is Ré. Sorry. We will send three different notes. Do, Ré, Mi. The spectrum is between 1 300 Hertz, 1 400 Hertz, 1 600 Hertz. Now we will send from speaker 1 a music composed with this note. Sorry. This is when speaker 1 sends this music. Listener 1 listen this music. Now, speaker 2 at the same time send his own music, which is a different music. And now listener 1 is not happy because he received the 2 music. Okay. Now we learn how to change the boundary of the room. And we found a boundary that made that now speaker 1 receive what listener 1 receives speaker 1, but does not receive speaker 2. And we can measure the degree of correlation, and it is very good. And of course, it is not speech, that in the room, two music are sent, two guys are receiving each its own music, because you have made a double ellipsoid in the room. Now, you can say it is strange, because you send three notes but spread in a spectrum which is much bigger than the coherence bandwidth of the room. And you will say it's strange. And in fact, what happened is that when we do the optimization algorithm, we have 200 pixels, that is to say, our 200 pixels on the boundary. And in fact, we try to create two ellipsoidal rooms, but at three different frequencies. It means that the number of degrees of freedom we have with 200 pixels is enough to transform the wall in 2 by 3 ellipsoid. Each ellipsoid is valid for one frequency, and it allows you to have a bandwidth which is much larger, but it is not a continuous bandwidth. It is a bandwidth, it is narrow band that you put in a large bandwidth, but it is not a full bandwidth. And now you can ask, can we do better? And this is what we are working in the lab with Fabrice Lemoult. Can we work typically with a speech that is between 30 Hertz and 5,000 Hertz? And the idea is to come back to the idea of time reversal communication in the following way. Instead of measuring the response between each element alpha, beta, and the pixel mirror, we will measure not at one frequency the response, but at many frequencies. Or it is the same to say we measure the impulse response. You imagine that each element alpha sends a click, short pulse, and you listen how long is the signal that you receive on a pixel element. And if you assume locality, but we will not speak of non-locality, but this can be taken into account, you will measure a set of impulse response between each antenna and each point. And you have many now time function, and it is equivalent to measure a multispectral matrix. Once you have this, you ask, what I have to put here to make a pixel of my mirror? Now the pixel of the mirror is much complicated, because you have an impulse response between alpha and E that spread in time. You have an impulse response between E and beta that spread in time. Now, one way is to put here a tunable filter. That is to say, when a signal is coming, you don't control only the phase of the filter at one frequency, but you have a filter where you can change the phase for each frequency. And this tunable filter has an impulse response. And if you put as an impulse response for this point, it is when you receive something, you make a convolution by an impulse response, and you send back as a reflected wave. If you do this, you are doing what we call a double time reversal mirror. Because if you know what comes from alpha to E, here you put a convolution filter that convolutes by the time reversal of H of alpha and E. And now if you add another convolution, but the time reversal filter from E to beta, but in fact, what is coming and coming back from this point arrive perfectly in phase in space and time. It's made the time compression and the phase focusing. But all these elements, how can you make them? There is a very simple way. Each element is a microphone that receives a signal, digitized, put in a convoluter, or not digitized, put in a filter, and after sent to a loudspeaker that send. And it is a mixture of this. And now if you put many of these elements here, each of them receive signal, make a convolution about what you want, and send back, you create a surface that now control for large bandwidth all the field. And the idea is that, in fact, you create what we call the double match filter. If speaker alpha speak through a random medium, for example, what you receive on E is a signal. If it is directly reflected when it's coming, it's a long signal. The echo coming from this small scatter is a long coda. Now it is written like this. Now, if here you add a convolution by this and this, which is the time reversal focusing. Now, if this point send this back, if you do this convolution, now what come back is a click. And you have also the effect of the spatial effect that allow you to refocus on beta spatially very nicely, because this medium plays the role of a lens. And when you have many of these elements, and when all these elements are activated, when you speak, well, there is the direct sound. But here, I just look what come back from the other part. You can really refocus very well. And we play on this first with ultrasound, because we have all the technology for ultrasound. We have two guys that want to speak to two other guys. We have an obstacle between them, and you have only the wall here, which is an ultrasound wall made of piezoelectric transducer that receive signal, we emit, convolute, and play with this. And we play with this. And first we learn, when one guy was emitting here, you want that it's come back here. You learn the good reflectivity filter that you have to put here. Now, if you send a series of pulse from one guy and another series from another guy, you want to see if R1 and R2 receive a good one. Now you can set noise from E1, from E2, and you want to see the noise you receive on R1 and R2 when you have created this sum of matched filter. It is a kind of ellipsoidal, sum of ellipsoidal at every frequency. And you look the correlation function you have. And what is quite interesting is the following, is that when you have your free space mirror, in free space, this does not work very well, because in free space, you have a very bad focusing. And if you want to send different sound to different guys which are close, the crosstalk would be very big. But if you introduce your random medium, the crosstalk become very small, and you can achieve for broadband signal very good focusing. And even a 16 mirror element, if you work with broadband signal, can be very impressive to send a lot of data to different guys independently for each guy. And this is what we call the matched filter optimization, but you can do better. You can do iterative time reversal or inverse filter. And we show that typically when we have 4 guys that speak to 4 other guys, we can found a mirror property that give you practically 4 channels which are independent. Of course, this is not very elegant because you have to put some electronics in the wall, and it is much more electronics than the one you put in a narrowband RIS. Here you put antenna that receive, antenna that transmit. But now for electromagnetic wave, this concept is interesting, because for electromagnetic wave, you can have kind of, you don't need really to play the role of an antenna that receive and that transmit. And there are people that look active, not perhaps ultra wideband, but RIS for microwave. And in fact, they can create reflection type amplifier. And if you receive a signal that goes directly in your reflected amplifier, it's come back, and you have not to have a full electronic of a receiving system plus convolution plus, but you have to introduce this reconfigurable filter. And in this case, you can really become a very broadband. Okay, I think, well, I am relatively in time, but I tell you about this ultra wideband is interesting really for sound communication. You don't need really today ultra wideband. UWB was very popular 10 years ago, and after 5G decided that it's better to have a narrowband frequency and to connect many of them instead of making an ultra-wideband system. But for speech, there is no other way. When you speak, it is ultra-wideband. And if you really want to play in a room, a scenario when I speak, somebody listen you and everybody, you have to be ultra-wideband. Nothing to do. You can divide the spectrum. Bon, this is a nice topic that we are looking for. Thank you for your interest.
We have time for 2 questions. Here.